Hi. Welcome to this session on deciphering data. My name is Pete Gallagher. I'm a freelance software engineer specializing in the IoT space mainly. I'm also a Azure MVP, Pluralsight author, and a community organizer here in the UK. So I like to keep myself busy. So we'll start out this talk with an introduction to IoT, just to lay the groundwork there, and then we'll look at some example IoT scenarios and some patterns for processing data. It's worth mentioning that this is actually the introduction to a much longer session, which I'll call out at the end. Okay, so we've got nearly limitless cloud computer storage resources, and we can control a vast number of devices now. And we've seen an explosion in AI technology, not only in the cloud, but at the edge as well. And devices like the Raspberry Pi and the NVIDIA Jetson are driving that somewhat. We've also seen an explosion in Industry 4.0 too, where digital twins are being used to map the environment around us. And we can use that information then to be able to help change our environments and our cities and our governments and even ourselves with things like wearables. So in this talk, we'll begin by looking at the example of smart factories. And here we could be looking at HVAC systems to be able to maintain a comfortable and healthy working environment, or perhaps maybe a lathe where we could be looking at a machine tool that spins at thousands of revolutions a minute. Or we could be monitoring the production line quality using AI and machine learning, or perhaps the actual raw materials that we've got stored somewhere. But this smart factory idea, we can apply that to pretty much any other IoT scenario we can care for. So at a high level, the architecture of an IoT solution is made up of three components. And firstly, on the left, we've got things that generate the data, perhaps devices that are monitoring the temperature in a factory or the manufacturing process, for instance. Onwards from that, we've got the insights, and that's based on the data generated by the things. And then finally, we have the actions where we take those insights and we can decide perhaps to turn the heating off in a factory when everybody's gone home, or send an alert because a machine needs attention. So we'll start here with the things, and then we can step through several different scenarios, starting with the simplest. And our first example is that of the HVAC that we mentioned a minute ago. And this device has got plenty of processing power, loads of RAM, and it can connect happily straight up to a cloud gateway, something like the IoT Hub, for instance, maybe a Raspberry Pi here. And this generates messages that can broadly fit into two different categories. So we can have telemetry, and that could be things like temperature and humidity. And then we can have alerts, and that could be, say, an emergency button's been pressed. And this message data is going to need to be serialized before we can send it to the cloud. And the data type for that is going to determine how we're going to serialize that. So say we're going to be serializing just temperature and humidity data, then something like JSON is going to be a really good choice for this, because a lot of the back-end systems, including IoT Hub, will natively support JSON, and you can then process that data directly there. For larger binary types, say like images or videos, then perhaps we want to choose something like Google Protobuf or Avro. But bear in mind, if we do use something along those lines, then there's going to be an overhead to pay in the cloud later to deserialize that data. And then finally, we'll nearly always include some form of message metadata to be able to determine, say, what type of message this is, whether it's an alert or telemetry, or perhaps the schema version or the device type and things like that. And we can use that then to partition the data later. Next, we can look at gateways, and gateways enable IoT communications across domains. And there are two types of gateways primarily. We have field gateways and custom cloud gateways. Field gateways are most often used when we need to integrate constrained devices that, say, don't have the necessary processing power to communicate directly to a cloud gateway. Something perhaps like a little Bluetooth environment sensor. Field gateways are normally co-located with these constrained devices at the factory level. So that is going to allow the constrained devices to talk directly to those field gateways. Of course, the manufacturing industry has got a long-standing history of embedded controller use with machine-to-machine communications over things like RS-232 and RS-485, and then using protocols like OPC UA and Modbus and so on. So the field gateway then ingresses the data from the constrained devices and sends it on to the cloud on behalf of those devices. Next up, we've got constrained gateways, custom cloud gateways. So custom cloud gateways integrate gateways across different protocols, different networks, different clouds. So a good example would be, say we've got a factory that's separate to our main factory that's storing the raw materials, but there's no internet access at that factory level, and we need to send the data to the main factory to send to the cloud. So at this point, we can actually use a custom cloud gateway across something like LoRaWAN and the Things network, and then we can process that data and then send that up to the cloud for processing later. Alternatively, we could use something like Sigfox or Particle maybe. Another thing to concentrate on in the Things area are intelligent edge devices. So we should look at why we'd include those in a solution like this. And one of the main reasons perhaps would be if we need some form of low latency response to events. So I mentioned the lathe before, and this is a really good example. This thing is spinning at thousands of revolutions a minute. Now, if say something like one of the ball bearings was to fail in that and it starts vibrating, if we're sending messages constantly to the cloud and we're processing it through an ML, an AI system, and then we're using that then to decide whether or not we need to shut the lathe down, that whole loop could just be too long. So what we really need to be doing is offloading all of that logic down to an intelligent edge device that can make those sorts of decisions locally and fast, so that we can stop that lathe immediately and stop it from spinning itself to bits. A good analogy here is our peripheral nervous system. So if you imagine you go and touch something hot and you immediately take your hand away from that, well, there are little nodes in your spine there that are controlling that sort of reflex action. And when your hand comes away from that hot thing, those nodes just send a message to your brain to say that an event's happened. So that's sort of a good analogy in that respect. Another good reason would be that this lathe is just sitting there spinning, and you might be monitoring its temperature and its number of revolutions per minute and torque, but for the most part that data is not changing. That's constant, consistent data. So what you can do is you can process that data down at the edge, and you can perhaps aggregate it together and then just send a block of data with the most important bits of data up into the cloud and deal with it later. Another reason is that perhaps we could be monitoring a production line. So we're taking either videos or still images. And again, that data is pretty consistent most of the time. And so we can train our ML models to run at the edge here to detect any problems. And only then do we send information up to the cloud. So now that we've got the IoT data in the cloud, we should move on and start looking at the insights. And the first thing we're going to want to do with this data is store it somehow, and we can perhaps partition this data by telemetry type, whether it's an alert or just telemetry, or the device type or schema. But storing all of this data in one place is generally a bad idea, because not only is it going to be slower, but there's going to be a cost implication there as well. So what we tend to do is, for data that you want to report on and against, and we store that in something called warm path storage, and that allows us easy access to it, but that generally tends to be more expensive. So for data that's just ongoing and we're perhaps going to use that to train an ML model later, we could put that in cold path storage. And that's going to be a little bit more difficult to get access to, but it's going to be far cheaper in the long run. Then generally, as this data is going to come in, we might like to transform it in some way. So it's possible that we could have multiple different schema types, and we need to normalize that in a way that we can then store later. On top of that, then, we might want to process this data in some way. So it might be that we need to apply some sort of business process in there, say the temperature's gone above 40 degrees and we'd like to do something with it. And then finally, obviously, we need to surface that data somewhere for reporting and UI. And so we can see there how the data's flowing through, and we can surface that. Onwards from that, then we've got the insights. Now we need to apply some form of actions. And we want to take the results of those insights and then feed them back in a loop so that we can make better decisions and automate device interaction and things like that. And we might also want to use that IoT data to train machine learning models, and then we can push those machine learning models back down to the edge. And so what you can see here is a typical IoT reference architecture, and we can see how the data is flowing through the system. So I mean, that's sort of the main part of what I wanted to get across. As I mentioned at the start, this is actually the introduction to a far longer session where we'll talk about data enrichment and partitioning and stream processing, where we're looking at Azure Functions and Stream Analytics and Databricks. And we can look as well at the storage options and how we can optimize for performance and cost. And we'll also dive into data visualization and exploration there as well. If you want to go on and learn a little bit more about this particular session, then you can hit these resources up that you can see on the screen. So you can go to aka.ms IoT 20 resources for the session resources hub, and you can get the code there at aka.ms/IoT 20. And then if data processing is your thing, then there's actually a curated set of Microsoft Learn modules that you can go and step through, and you can get those at aka.ms/IoT20/learn. This session is sort of heading you towards the AZ220 IoT developer certification, which is a fantastic way to up level your knowledge in IoT, but also it gives you that extra professional edge if you perhaps want to make a sideways step into IoT or progress your career a little bit further. So you can find out a bit more about the certification at aka.ms/IoT20/certification. And if you start taking that, then there's some fantastic resources for you to use as well. Paul DiCarlo's made a fantastic study guide for the exam there at aka.ms/IoT cert guide. There's also myself and a few other great authors authoring some Pluralsight content to be able to take you through in a more visual way. And you can get that at bit.ly/Pluralsight-AZ220. And also, don't forget that we've got the 30 Days to Learn It challenge happening at the moment. So there's never been a better time to go and learn stuff. And the content over on MS Learn is a great way to do that too. So thank you very much. Thank you for tuning in.